whatever you prefer, guys. Okay. Yes, even though I'm thinking that maybe some laters are still coming, but I don't know.
Can it be open from outside?
Yes, yes, it can. Yeah, of course.
You never know.
This is a jail, but for the rest of the world. Nobody can get in.
I say it just because maybe people walking here. I mean,
no, sure.
they disturb us and we disturb them.
If you leave it like this.
Right, maybe just.
I mean, I'll close it when I finish the presentation, no problem. Okay, so let me introduce Mélanie just like with few sentences. And I just realized that this is horrible. I'm talking about your life, but here this is like the worst mansplaining that somebody can do. But anyways, so she did her master in the University of Pierre and Marie Curie. Then she graduated from her PhD from the
CEA.
Yeah, CEA, I remember. Saclay.
Yeah.
Saclay?
Exactly. Yeah.
Okay. Institution. And she's currently a postdoc in the Heidelberg University and a group leader. So we are very lucky to have her as an expert on star formation. So thank you, Mélanie. And whenever you want to start, please go ahead.
Thank you very much. Good morning, everybody. I'm very happy to be here today. It's almost intimidating to give a seminar in front of real people after almost 2 years. So that's why I'm very happy to be here. And I'd like to talk today about how stars form, and specifically about the cycle of matter in galaxies between gas and stars, and how we can constrain this cycle from new high-resolution multi-wavelength observation of the nearby galaxy population. So I'd like first to start on the large scale, on the cosmological scale. And you see here simulations where each blue blob here is a galaxy. And gas is accreting on these galaxies over this very large scale filament, so this in green here. So on these large scales, galaxy growth and galaxy evolution is regulated by the balance between this gravitational inflow on the galaxies and the feedback from the galaxies. That you can see the hot gas being expulsed outside of the galaxy back into this intergalactic medium. But now if we zoom in on one galaxy, this is where the stars form, and these are the sources of this feedback. So stars form in the center of cold, dense molecular clouds, which you can see if you follow an overdensity of gas here. You can see as it condenses, get denser and denser, and then you can see at some moment the gas being expelled under the effect of the star formation and the radiation from the stars. So if we just decompose this process of star formation, so we see galaxies through their gas and stars, but what do we see exactly? We see a background of diffuse interstellar medium, and in them, giant molecular clouds. Under the effect of gravity, these giant molecular clouds condense to denser and denser structures. And in the center of these dense structures, stars form. And throughout their life, stars emit radiation and winds. At the end of their life, the massive stars can explode as supernova. And this is what we call the stellar feedback. And this is really one of the main points of this talk here. So I'm going to discuss that in detail later. But of course, these processes take place over many millions of years, and we can't see that in observations. So we go to simulations. So you see, as we start with a giant molecular cloud here in orange, it condenses, stars are forming, so in blue, and they expel the star and the remaining gas. So this is the stellar feedback. And the gas that has been heated and exposed from under the effect of the feedback will later cool down, condense again, and form new stars. So schematically, this can be represented as a cycle where gas accretes on the galaxy, the diffuse medium condenses into cold gas clouds, molecular clouds, stars are forming within them, the stellar feedback, so radiation, winds, and supernovae disrupt the molecular gas back into the diffuse interstellar medium, and clouds can also be destroyed or dispersed by dynamical processes within the galaxies. The combined effect of the stellar feedback in the galaxy can also push some of the gas back outside of the galaxies, where it will later cool down and later accrete again on the galaxies. And this cycle happens like this again and again. But the big questions are really what fraction of the gas is actually condensed into molecular clouds, what fraction of the gas is condensed into stars, on what timescale that this happen, what energy do you need to disperse the gas? So in the end, so the question is, what are the mass flows going through this cycle? And that, again, we can't see observationally. So we need to go to a simulation for that. But this is not that easy, because actually from simulations, it's maybe even more difficult to solve these questions. Because star formation happens, I already said, on a cosmological context. So we start from very, very large scale, 10 to the 5 kiloparsec here. As gas accrete on the galaxies, we can zoom in into one star forming region. Within these star forming regions, we form cold cores within which individual stars are going to form with their protostellar or protoplanetary disks. And all these scales are connected through feedback, as matter and energy is redistributed from the small scales to the larger scales. So it's 12 orders of magnitude here that are covered, and all these scales are important for star formation. And it's not only spatial, but also each step covers different time scales, from the explosion of the supernova, which happens into a couple of years, to galaxy formation and evolution, which takes billions of years. So here it's 9 orders of magnitude that you need to cover in time if you want to model from first principle star formation and feedback in galaxies. So computationally, it is impossible to model this matter cycle from first principles. And to go beyond that, models and simulations require sub-resolution prescription. So basically, they're going to model that part, and everything that is below on smaller scales is going to be described input as ad hoc prescriptions. The problem here is that these prescriptions are unconstrained observationally. So from observations, you get basically the end results. And we know, for example, that there is a strong relation in galaxies between their content in gas and their star formation rate, how fast they're forming stars. So, okay, we know that from observations, but how you get there is very difficult. From galaxy, we can simulate galaxies with identical conditions, but different criteria for which gas is forming stars. And we will arrive on this relation, but with very different morphologies, as you can see in these 3 examples here, very different properties of the modeled galaxies and their internal structure, etc. And all of these assumptions make sense, and we don't know a priori which one is correct, which one happens in the real universe. And it's the same thing for feedback. So again, 3 different examples with identical conditions. We don't know which is the dominant feedback mechanism. So it can be supernovae, it can be photoionization, and it can be a combination of the 2. All of this actually makes sense, but you can see that the end result is going to be completely different. So if we want to make galaxy simulations predictive and connect them to the observed galaxy population, we need an accurate description of the cloud scale physics for star formation and feedback. And the only way to do that is to go back to observations, to the real universe. So because the resolution that we get from the observations and the fact that these different mechanisms combine in a nonlinear way make it really impossible to model from first principle the star formation and the feedback. So we're going to try and get this physics of star formation and feedback from the observations. But what do we really mean by that? What are these physics of star formation? Well, there are very fundamental questions that we want to answer. First is, how do the gas clouds in galaxy collapse to form stars? Do they just collapse under their own gravity, or are they supported by magnetic field, for example? Then about feedback, which feedback mechanism helps star formation? I've talked already about supernovae, photoionization, stellar winds, can be a combination, a nonlinear combination of all of these mechanisms. And finally, what is the resulting rate and efficiency of star formation? So from observation, we know that star formation rate and gas are related, but we don't know what is the star formation efficiency, and we don't know on what timescales this happens. So observationally, these two quantities are unconstrained and they're degenerate, right? So we don't know if star formation is inefficient and fast or efficient and slow. Most of these questions can actually be solved if you're able to measure the timescales on which all of these steps happen. So how long it takes for the clouds to collapse, how long it takes for the stars to disrupt the clouds. So in the following, I'm going to show you how we can measure these timescales from observations, and how these observations will motivate the next generation of subgrid physics of star formation and feedback. So these questions of how long clouds live has been a long-standing problem. And many studies have suggested seemingly contradictory values for more than 100 of megayears, based on the fact that we see molecular clouds sort of everywhere in a galaxy, also between spiral arms, where most of the star formation happens. Other studies have counted clouds, so clouds without stars, clouds with some star formation, clouds that are ongoing disruptions. And by these relative numbers, they have inferred 10 to 50 megayear timescale for the clouds. And finally, specifically in the center of our galaxy, in the central molecular zone, by following gas clouds along a known orbit, some studies have inferred a 1 megayear lifetime for molecular clouds. So up to now, it has been unclear if this variety, so about 2 orders of magnitude, is actually physical because we're looking at different environments, or if it comes from differences in experiment designs and subjective cloud classification, which often requires to resolve clouds. So I'm going to present in the next few slides a new approach to measure this cloud lifetime. We cannot just obviously look at how long clouds form because it takes millions of years, but we can ask the question in a very basic way with 2 extreme cases. Are clouds living for very long, or are clouds living for similar timescale as massive stars, so a couple of megayears? In other words, do we have a quasi-equilibrium or a rapid cycling between gas and stars? What that would mean is that in the first case, clouds form stars over many dynamical time, and in the second one, clouds are rapidly destroyed by massive stars. And what you would see observationally is that in the first case, gas and clouds are correlated on a small scale, so they're co-spatial. And on the other case, gas and stars would be decorrelated. They would almost never be co-spatial. So what do we see from observations? I'll take the example of this flocculent galaxy here, nearby galaxy, NGC 300. It's a very regular galaxy, so it's sitting on that Schmidt-Kenniker relation here, linking gas and stars. And so what do we see when we look at basically a tracer of the young stars, so in H alpha, and CO, so a tracer of the molecular gas. I'm showing here in this panel the ratio between these two, so between gas and stars. And here is what we see at low resolution. So you see that at low resolution, this map is pretty homogeneous and sort of white. So you don't see bright blue or bright red, right? So this translates the fact that gas and stars are correlated on the large scales. But now what do we see when we go to higher and higher resolution? Do we see a correlation still a correlation between gas and stars, or a decorrelation. And if we see a decorrelation, we'll see gas regions with only gas, so very blue, and regions with only stars, very red. Otherwise, it will still stay whitish. So you can see you will see very rapidly that with new ALMA observations, when we increase the resolution, you go from this white map to very dark blue regions and very dark red regions. So a decorrelation between gas and stars. And this translates a rapid cycling between gas and stars, or rapid destruction of the clouds. The last panel here shows a way of quantifying this decorrelation. And by fitting this diagnostic plot here with the black lines here, we have developed a model that with which we can fit these observations and get the cloud lifetime, the feedback time scale, so how long it takes for the stars to disrupt the cloud, and the typical separation scale between individual regions in a galaxy. And from this 3 parameters, we can derive other interesting quantities such as the star formation efficiency, the coupling efficiency between the feedback and the gas, etc. I will come back to that later in the talk. But to come back to this galaxy NGC 300, we have applied this method and fitted the observations of the gas to stellar flux ratio as a function of scale to measure the cloud lifetime of about 11 megayears, a feedback time scale of 1.5 megayears. So it's relatively short. These two, if you compare to the numbers I've mentioned earlier. Typical distance between individual regions in this galaxy is about 100 parsec, and we have a star formation efficiency of 2.5%. So this is quite low. Only 2% of the gas cloud is converted into stellar mass. Now that we have been able to measure these quantities, for the first time we can do that in a systematic way throughout the galaxy, and not only get one value, but also how these quantities evolve in the galaxy as a function of distance to the galactic center. And I just want to focus into a couple of important quantities here. So first, the cloud lifetime. So you see that it's relatively constant in the galaxy. And what is interesting is that it's pretty close to the free fall time. It lies between the free fall time and the crossing time. So there is no need for additional support by magnetic field, for example, but clouds collapse under their own gravity mostly. Then the feedback time scale, so 1.5 megayears, I said it was pretty short. And that's mostly in comparison with the time scale, the characteristic time scale for the first supernova to explode, which is 3-4 megayears. So you see that the clouds are actually already dispersed before the first supernova explode. And this is mostly due to photoionization and stellar winds. Then another quantity that is interesting to look at is this typical distance between regions. And we have compared this to the gas disk scale height. So basically the width of the gas disk. And you see that there is a very good correlation. And this is a sign that star formation is feedback regulated in this galaxy. So if you have star formation that is emitting radiation and winds, it's going to expand. So you will see a bubble, so blown by the feedback, expanding. And when it reaches the side of the gas disk scale height, the bubble will depressurize, right? There is no gas to push anymore. So the bubble depressurizes and set the typical distance between regions to the gas disk scale height. So we've been able to bring a couple of constraints on this matter cycle in galaxies. So how long it takes for gas clouds to form stars, how long it takes for stars to disrupt the clouds. But we've done that only for one galaxy. But this is not enough. We know there is a large variety of galaxies in the universe. So we don't know if these numbers are going to be the same. And for that, we have now applied the same analysis method to the galaxies of the Fung survey. And this is, the team of people that have participated to the observations. We have collected a large number of galaxies of observations at high resolution, so about 50 parsec, between 50 and 100 parsec for 74 galaxies with ALMA. We also have Hubble observations, Muse observations for 19 of them. And very soon we'll get corresponding JWST observations also for these 19 galaxies. So we're really covering the entire electromagnetic spectrum for a large number of galaxies in the nearby universe. For 54 of them, we have already measured the decorrelation between cold gas and young stars, and we see that this is universal. So in all of these galaxies, you have a rapid cycling between gas and stars. And so with my team, and in particular, this is the work of my PhD student, Jaeyeon Kim. She has measured this cloud life cycle in all of these galaxies. And you see the wide diversity of cloud lifetime and feedback time scale here. And to see that a bit better, I'm showing here the histograms for the cloud lifetime. It's relatively short, between 5 and 32 megayears. The clouds are efficiently dispersed by stellar feedback between 1 and 5 megayears. So again, mostly before the first supernova explodes. And star formation efficiency per cloud is low. Only 1 to 6% of the cloud mass is converted into stars. Yes.
Could you explain a bit how you get these parameters? Because I understand that you measure this correlation, but how do you transform that into physical?
Yes. So basically, I can come back to that maybe later. I think I have additional material to show, but basically, so this model here, so the green line that you see here, it's an analytical model, and there are only three parameters that entirely describe this model. So we feed this model, this analytical model, to the observations here of the gas to stellar flux ratio. And the three parameters are the one that I've talked about. So the cloud lifetime, the stellar feedback, and the typical distance between regions. And only with these three parameters, you can completely describe this behavior here. Does that answer your question?
Sure. Yeah, but I guess I was wanting to say the details of how those things, how you end up predicting these curves, but we can talk later.
You wanted to add something?
Well, do you have the other movie in your backup slide?
Yes. Yeah. So this is for simulated galaxies. And this shows you, so again, the ionized emission, the ionized gas emission, so the stars, the gas, the ratio between the two, and this diagnostic plot here. And so for this simulated galaxy, we know how long the clouds are living, what the feedback time scale is, and of course, we know what distance is between each region. So you can see that, is it playing now? Up. Yes. So by changing, and so the first thing that you can change is how long the stars live, right? You see that you have more or less emission peaks here, and you see how the asymmetry between the two branches changes. By symmetry, you can do the same for the cloud lifetime. So if you change the cloud lifetime, the number of clouds emission peak here changes, and the asymmetry between the two branches changes as well. And the feedback timescale, so the overlap between clouds and gas, plays on the flattening of the two branches. So if it's longer, you have less decorrelation. If it's shorter, you have a larger decorrelation. And finally, the region separation length is governed by when the two branches decorrelate. So this is going to, so by fitting the observation, this is going to fix this, the three parameters of the model. Oops. So I was here. Yeah. Yeah, so we have this low star formation efficiency and short cloud lifetime. So in the end, we can say that star formation is fast and inefficient. But then we can try and look a bit more closely to these timelines. And we have noticed that, you know, this orange part of the timeline, so where there is only gas and no stars yet, is pretty long. There is it's about 70 to 95% to 90% of the cloud lifetime where we don't see stars. So it looks like the cloud is inert during this phase. And so to really investigate that, we have looked at whether this cloud was really inert. And to do that, we went to infrared observations, right? Because we know that when stars are very young, they're embedded between the gas and the clouds, and you don't see necessarily H alpha, but you can see infrared associated with the gas clouds. So you can add this additional phase here of embedded star formation. You can apply exactly the same method with CO and infrared emission. Here we've used 24 micron emission. And you can add another component here. So it's CO, 24 micron, and H alpha. And you see there is indeed part of the timeline here where we see 24 micron emission, so embedded stars without H alpha. And this embedded phase is between 1.4 to 3.8 megayears. So the cloud is not completely inert during this phase. We have done that only for 5 galaxies or 6 galaxies at the moment. But now with that, we have the approved James Webb program, so a large program with the James Webb telescope. So we'll be able to multiply by 4 this sample and add 19 galaxies and really start to understand how this timescale vary with environment between galaxies, for example. Now, if we come back to the full timeline, so we have, again, a short cloud destruction timescale. And this is what I would like to focus on for the rest of the talk. So we have variation between galaxies, but a relatively short feedback timescale. And I'm going to focus into a subsample of these 54 galaxies, so 9 galaxies for which we have done more in-depth analysis of this feedback timescale. So the first thing that we noted is that there is a correlation of this feedback timescale with environmental properties, and the strongest one is the correlation with the stellar mass. So to try and understand why this quantity vary, why we have this quite large spread of feedback timescale and why it varies with the stellar mass, we have compared our observations with theoretical prediction for this feedback timescale. So the first thing that we can compare with is obviously the supernova delay time. So when is the first supernova going to explode? And this is between 3 and 15 megayears, depending on the stellar region mass. And then we can compare with what I call early feedback mechanism. So they start from the beginning, from when the stars are born. And this is photoionization, stellar winds, and radiation pressure. And I'm not going to go into the details of these equations, but what we do is to solve for this equation here. So we know how, given the density of the cloud and other properties, we know how fast the bubble expands analytically. And so we solve for the time at which the size of the bubble blown by feedback equates the radius of the cloud. And then we consider that the cloud is destroyed. And this gives us the characteristic timescale for each of these mechanisms. So now we go and compare with observations. So I'll plot here on the y-axis the predicted feedback timescale, and on the x-axis the observed feedback timescale. So the one-to-one line is here. So if the data points are above the line, it means that the predicted mechanism is too slow. If it's below the line, it means that the predicted mechanism is fast enough and potentially can destroy the clouds. So we can do that with predicted feedback from supernova. And we find that for almost all of these galaxies, it falls above the line. So the supernova explode, the first supernova explode when the clouds is already gone. If we do that now for early feedback mechanisms, so the minimum between photoionization, stellar winds, and radiation pressure, now we are below the one-to-one relation. So either photoionization or winds are fast enough to destroy the clouds. So these pre-supernova mechanisms really play an important role in dispersing the clouds, but you can see that they're almost too fast in a way. They could potentially destroy the clouds faster than what we observe. So what this means is that their coupling efficiency with the gas is not 100%. Some of the energy is lost, right? Maybe because the clouds are porous and some of the wind or photons can escape the clouds without destroying it. So by measuring the distance between the one-to-one relation and the data points, we can measure this coupling efficiency. And before I go there, so if you remember this slide that I showed at the beginning of the clouds, whether supernova, photoionization, or a combination of both are important in destroying the clouds, now we can say that supernovae only are probably not the right answer. And you need photoionization, maybe combination with winds as well. But you see that this already excludes part of the parameter space for simulations. So now going back to the feedback coupling efficiency, we measure a coupling efficiency of between 8 and 50% approximately, so a couple of tenths of percent, which is qualitatively similar to simulations, although a detailed comparison is difficult. And the fact that this is relatively low, so it means that there is a large fraction of the energy that is going out of the clouds, right? And that potentially ionize the gas outside of the clouds on large scales in galaxies, which explain, at least partially, the observed diffuse ionized hydrogen emission that we see in nearby galaxies. Then we've looked at environmental dependencies, so with the metallicity, and we see that if you exclude that one point, there is a decreasing trend of the coupling efficiency with decreasing metallicity. And this makes sense. This is what we expect for that, because we know that gas is more porous at low metallicity. So therefore, a lower coupling efficiency. And finally, we see almost no trend of this coupling efficiency with the GMC surface density, which tend to indicate that it's photon leakage rather than radiative cooling that likely dominates the energy losses during this feedback phase. So to just summarize this part on feedback, I've shown that early feedback mechanisms, photoionization and winds, are efficient to disrupt the clouds before supernovae. We have an average coupling efficiency of a few tenths of percent during the feedback phase, and environmental variations with galactic properties. And this is important. We've seen on this simulation that this really has consequences on the structure of the galaxies, but also how the matter and energy is redistributed in the galaxies and how this can affect subsequent star formation. So with these measurements, we can now determine in which environment supernovae explode, and this is important to also understand what fraction of the gas will be sent out on what scale the supernova can redistribute the gas and input some energy. We can also time resolve more finely, so this time scale for star formation and feedback. I've mostly talked about here molecular gas clouds, so CO and H alpha, but with MUSE and now very soon JWST, we will be able to really refine this time scale and cover every step of star formation and feedback. And this we've already done in the LMC, because so this is the our closest neighbor. We have a lot of observations of the LMC. And so by applying the same technique to different wavelengths, we have been able to measure how long it takes for the gas cloud to assemble from this diffuse atomic medium. And you can see, so in this H1 gas in red here, and you can see that it takes quite a long time for the clouds to assemble, right? You see the rotation of the LMC here as it has been measured with Gaia. And it really takes a long time before you see for the first time, CO, so molecular clouds really. And then very soon after that, some embedded star formation in blue, so in infrared, and then H alpha, so non-embedded stars, and then ionized radiation from gas that is heated by the stars. So sulfur 2 and O3. So with this type of observations, we'll be able to not only have these two components here, but also how clouds form and assemble, and also time, like refine here this process, which is not just in 2 or 3 phases, but we can really decompose that with many different wavelengths. And finally, with this type of observation, we can test subgrid physics that are used in simulations. And we've done that already for a couple of simulations. And the first thing that we can look at is whether this decorrelation between gas and stars that we observed in galaxies like NGC 300, do we also see that in simulations? So do we have this rapid cycling also in simulations? So we've looked at a simulation here where the feedback is, there is a detailed feedback mechanisms from supernovae and photoionization. All macroscopic quantities of this simulation match observations in terms of star formation rate, galactic mass, depletion time, etc. But also cloud properties, cloud radius, cloud mass, velocity dispersion, also very well reproduced observations. However, when we've tried to look at decorrelation between gas and stars, we almost saw none. So basically the clouds were sitting there, forming stars over and over and over, and never get destroyed. So you see that the 2 branches here, this is from the simulations, the 2 branches are very flat, which shows that there is no decorrelation between gas and stars. And the other one with the dotted line here are unobservations to compare. So NGC 300 again. So you see that there is a big difference here. We don't see a rapid cycling in the simulation. So these quantities that are very well reproduced are reproduced for the wrong reason, right? It's the wrong mechanism that are generating stars and feedback in this simulation. So we've tried to improve this with improved photoionization here, basically inputting more energy from the stars into the gas. And this is enough to generate this decorrelation. Basically, now that we've improved the photoionization, that we've generated more energy, the clouds are being destroyed and we see this decorrelation. And this, again, matches pretty well unobserved galaxies like NGC 4254. So you can see how we can use this technique to check a posteriori simulations and try to improve it, but we can also go a step further and directly input what we have learned from observations into simulations. And this is what this empirically motivated physics suite of simulations is doing. So we've taken directly and the input momentum that is set by measured quantities to generate early stellar feedback in the simulation. And I'm comparing here two simulations. So one, which is only using mechanical supernova feedback, and the other one is also using this empirically motivated feedback. First thing that you see is that the structure, the morphology of the galaxy is quite different. Here you have big regions, so big holes, and the other one is more homogeneous in a way. And the result of that is that if you look at the decorrelation between gas and stars, in the first case, there is a slight decorrelation, but it's quite far from what we see in observations, which are in gray here by comparison to the LMC. in the second case, we do reproduce the decorrelation between gas and stars. So by construction, we reproduce the cloud life cycle that is observed in the real universe. So yeah, we have described, with the observation that we have now, we are able to constrain this matter cycle in galaxies from the observations. We can also do that in simulations, compare both, and try to improve the simulation that we currently have. So coming back to the three questions that we had at the beginning, so how do clouds collapse, which feedback mechanism help for star formation, and what is the resulting efficiency of star formation? Now we have the answers from observations. Cloud lifetimes are between 5 and 30 megayears. They are environmentally dependent. Clouds are destroyed by photoionization and stellar winds before supernovae, and star formation is fast and inefficient. So in the near future, we will extend this measurement to cover a wide variety of galaxies, including different morphologies. So, we've mostly looked at spiral galaxies for now, but we will also look at early type galaxies, at higher redshift galaxies as well. With so now the MUSE data, but very soon the JWST data, we will be able to time resolve the timeline for star formation and feedback, test and improve subgrid physics used in simulations, and finally determine the mass flows through the matter cycle, both in observations and in simulations. So I've added here just, the observatories that you can use, the different facilities that you can use, and you can see that we really cover the entirety of this cycle, and we'll be able to determine what part of the gas goes into the stars, what energy is input from the stars to destroy the clouds, and how gas condenses from the diffuse interstellar medium. So thank you for your attention, and I'm happy to take questions.
Questions? Danny?
Okay, so regarding the parameters that you obtained from fitting the model with the three parameters, do you have something in which we can see the values obtained for the different 50 galaxies that you used to calibrate the model? So to see the dispersion of the values that you were obtaining?
I'm sorry. So I think this is what you mean here.
So all of the galaxies that you used were elliptical, were spiral galaxies. So
they're mostly spiral. Some of them are more flocculent. So between flocculent and grand design, we have a bit of dispersion, but yes.
And could you apply these parameters that you calibrated with that also for elliptical galaxies, or do you expect that the behavior is very, very different? Or how it would compare to that?
Yeah, this is very interesting. We have so I have an ALMA program to observe. Well, these galaxies have been observed. We have, I think, six galaxies, elliptical galaxies. It's more difficult there because their disk is smoother when you look at them, so you don't really have these gas emission peaks, which and stellar emission peaks to see how their correlation or decorrelation evolves with spatial scales. And the other difficult thing is that they're often further away from us. I mean, there is no elliptical galaxy that is really nearby. But we still have managed to have, I think, 5 or 6 elliptical galaxies. We have not looked at them yet.
So it's that in principle you could apply this model to that, but observationally it's been difficult to use them for the analysis.
Yeah, it's been difficult already to get the observations at sufficient resolution and sensitivity. Yeah, but we'll do that soon.
So I was wondering something similar. So if you select galaxies that are outliers in the Kennigat-Schmidt relation.
Yeah.
Like, do you expect like a different decorrelation of the branches, or like some kind of different weights in the feedback mechanism of the galaxies? Or did you try them? already?
Yeah, I think that's what we would expect. There are different reasons why galaxies would be outliers on the Schmidt-Chemical relation. For example, you can have starburst, which here we could not analyze this way, because in starburst galaxies, basically you synchronize all the star formation to happen at the same moment. And what we need here is a relatively smooth star formation history, so you can really probe all moments of the timeline of the cloud lifetime. But yeah, the goal, and that this is something that we're looking here also with my PhD student at really why do we see this variation? Is it correlated with galactic environment? So for example, specific star formation rate or stellar mass. So we do see a slight correlation with stellar mass, but it seems that it's a little bit more complicated than that. Maybe it's a combination of several things.
And the second question is, as far as understood, you measure the decorrelation within a simulation run with ENSO code, right? Did you try to measure this decorrelation also with other hydrodynamical codes or separate processes?
So this simulation here is using a repo. We have a plan to apply the same method to other simulations run by other groups. So we're in contact. We're in contact with other groups. Yeah, but this is in progress.
Thanks.
It's kind of in the line of what Giovanni just asked. So I as far as I understood, you showed that, yeah, there is simulation generally do not reproduce the decorrelation that you observe. Is that right?
Some simulations
some
do not
simulations,
indeed, yes.
So and by including this photoionization feedback, then you can actually improve this aspect.
Yeah.
I was wondering whether this has repercussions on the global parameters, for instance, of the galaxy or the star formation history or the metallicity gradients, for instance, on simulated galaxies. Because if those were fine, let's say before changing the model, I would expect that the improvement should also preserve.
Yes, indeed. So here, it preserved the global properties of the galaxies. And in this simulation here, so where we directly put from the observations the input momentum that we calculate from the observations, this simulation here, so which has supernovae and empirically motivated feedback, reproduces very well observed galactic properties. So in terms of their star formation rate, galaxy mass, etc. So yes, we do pay attention that the global quantities are also preserved.
So just a further question. So in this case, can it be summarized in some way as a displacement of star formation with respect to molecular clouds, with respect to the previous simulation? So as I understand, star formation and molecular clouds were spatially correlated previously, while in your model they are decorrelated, right? Then in general, let's say the star formation history and properties are consistent among them, if I understand correctly.
So the way, I think the one way of understanding it is, so in this simulation here, you can see that you have very dense regions where many massive stars are going to form and where supernovae are going to explode in a clustered way. So which is going to generate these huge empty bubbles here. And this is going to also quench star formation in a way, but in a much more violent way than in the other one, where you have smoother feedback all along the lifetime of the cloud. So yeah, it's a change of how you input the energy in the galaxy, whether it's in a clustered way or whether it's in a more dispersed way. Yeah.
Okay, thanks.
Yes, a very good question now. So what? So now your new feedback that depends on, I guess, an efficiency parameter, a time scale. What is RCL? That's, I guess, the main difference with field processes, right?
RCL is the size of the cloud.
Okay, so you need to somehow identify clouds, and the bigger the cloud, the more energy.
That's so all of this we calculated from observations at the blue quantities. So these are average quantities for the 9 galaxies that I've shown previously. On this, so input momentum, analytical input momentum here, the only free parameter would be this alpha, which varies between, which can physically vary between 0.5 and 1. But we've done some tests and basically doesn't change much the resulting input momentum here.
Now in a simulation, usually you have a threshold for star formation. Right? You assume that a given
yes.
normal cell or state particle will form a fraction of it. Stars when it's above certain threshold. So in your recipe, I guess you also have the same star formation, but then you assume that for every dynamical time, there is a fraction of the mass that is released in form of energy.
I'm not sure I can get your question, but for every stellar particle that we form, so from when the stellar particle form, we input that momentum, we inject our this momentum at the spar at this.
That momentum is just has some free parameters, and it's but it still depends only on the amount of mass that's being formed in stars, and after some time you release some part of the energy. So I'm confused.
So
how is it different from what people have done?
It's not that it's necessarily different from the mechanism is not really different, but the amount or the quantity that this input momentum is based on is really from the observations. So I think this is the main result here, is that we show that if we calculate this input momentum not based on what we know from the winds or photoionization, but if we really calculate this momentum from what we see in observations, then we get what we expect, and we do reproduce the observed cloud life cycle.
Because instead of trying to reproduce directly the chemical Schmidt, you just say it's space.
Yes. Yeah. And so and by doing this, we kind of take out the subjectivity of trying to get to combine in a nonlinear way. Because normally you would need to combine winds and photoionization, and in a nonlinear way, and all of that is subgrid. So it's kind of difficult. We just take what we see from observations.
Okay. And then I guess you mentioned that you calibrated your analytical model on hydrodynamic simulation, right? Or not?
No.
Okay, so it's
the model that we fit here.
Okay, I find the Nature paper, no? So again, the analytic model has no free parameters other than the.
Maybe what you mean? Yes. So there is one thing that we indeed calibrated. It's maybe I come back here. The one parameter that is calibrated is the duration of the H alpha lifetime here. So for how long do stars emit in H alpha? And that we have indeed calibrated from stellar population synthesis models to be, I think, 4 something 4.3, I think, mega years. And it depends on the metallicity. So we take that dependency into account, but it's we're very well calibrated.
And then in the cases where you saw a discrepancy in the correlation function, I don't know if we could. So you actually recover correctly the lifetime of the molecular clouds on that particular simulation?
So
if you apply your analytic model, then you say, okay, like
so yes. Yeah. So I mean, we've done that in two separate, two distinctive steps, basically. But first we have calibrated this duration of the H alpha lifetime. But then we have also applied this method to simulations. It can be, we've done that for several simulations actually, to check that indeed if we know the timescales in the simulation, we apply this technique, then we recover the timescales of the simulations. Yes.
Okay. Because I would remind that the correlation does not only depend on those parameters that you were mentioning, but also depends on the spatial distribution of the DMCs.
Yeah. And this is the third parameter here. So lambda,
okay.
Which is basically the distance, so not only between molecular gas, but basically between any peak, whether it's star forming or whether it's a gas peak, any peak. And yeah, this is indeed an important parameter of the model, and that's what governs at which scale these two branches decorrelate.
Okay, thanks.
Any more questions? Okay, Marcos.
When considering the photoionization, the radiation pressure feedbacks, and in general, not the supernova feedback, do you consider feedback from nearby molecular clouds or conditions outside of the molecular cloud?
Yes. So if you're talking about
Like the feedback, it's computed with neighbor, it's more globally computed.
Yeah, so if you're talking about this timescale, these analytical timescales here that we compare to, it's internal. So it's how a cloud is going to be destroyed by the stellar population inside this cloud. The distances that we measure, so between individual regions, so this lambda that I was talking about, is typically a few hundreds of parsecs. We don't expect a region that is located 100 or 200 parsecs away to be able to really destroy a nearby cloud, or or completely disperse a cloud that is 200 parsecs away from that region.
Yeah, I was thinking like clouds closer to the nucleus of the galaxy, or some more extreme, environmental scenarios.
Yeah, so maybe where clouds are closer together.
Yeah.
I guess that could be potentially an effect.
Disk scale height, I think that typically doesn't happen for that reason, for what you explained earlier.
Right.
Right. It's a really good question. It's a good idea. I think towards centers, indeed, clouds get closer together, but the scale height of the disk gets smaller too as you get closer to centers, which means that the feedback bubbles depressurize earlier. So they depressurize when they reach a smaller scale. So as long as the clouds or the regions are separated by more than the disk scale height, then what you're saying should typically not happen.
Yeah.
I think, but you probably should measure it.
I guess I guess on average, I mean, you can always have by coincidence like two clouds that are going to be sitting next to each other and influence each other. But one of the strengths of this method is that it's statistical. So you're going to get what is dominant in the galaxy. Whether this can happen locally, maybe, but globally, we don't expect that.
Okay. The last question. Last minute question. Oh. Okay, then let's thanks. Sorry. Oh, yeah.
Zoom, I guess, was Nate and Stevie.
Yeah. Well. Yeah. No, it seems not. No, no questions from the internet, even though there's a delay. So maybe they are still with the previous question. But anyways, okay. So let's thanks Mélanie again, and thank you for the nice talk.
Stop sharing.
Yes, stop sharing. And I see myself. Hello, ma'am.